So for the first week or two, what I plan to do is to explain to you why people care about matroids and what are matroids. Okay. And so the first thing we're going to do is talk about some motivating examples for matroids. The first example comes from linear algebra. So what I'm going to do is, first of all, draw a configuration of vectors in 3 space for you. Okay. So here's R3. These are the coordinate axes. In fact, let me draw them like this. Okay. And I'm going to draw a bunch of vectors for you. So this is the first vector. Coordinates 1, 0, 0. Okay. The second vector, which we're going to call B, has coordinates 0, 1, 0. The third vector, C, has coordinates 0, 0, 1. Okay. Yep.
Shouldn't A go where C is?
Oh, whatever.
It just doesn't matter, right?
I'm sorry?
I'm just used to the first coordinate being the x-axis. He's being selfish.
Oh, I see.
I just got used to that. But no, that just
So-
doesn't matter.
Right, so Vladimir's complaint is that I'm not using the right-hand rule. It says that A cross B should equal C. But maybe I am, and C is pointing into the board. Okay. In fact, that's exactly what's happening. C points into the board. I meant to do it that way. A cross B. Vector D is going to be the midpoint here. So, and of course, the midpoint of this segment has coordinates 0, a half, a half. Okay. Vector E is twice vector D. It has coordinates 0, 1, 1. And vector F is just the origin, the 0 vector. Okay. So there are 6 vectors, A, B, C, D, E, and F. And imagine that I give you a task. It's a task which you can accomplish in many different ways. But what I'm going to ask you to do is to choose a set of linearly independent vectors. Choose a set of linearly independent vectors. Okay. And of course, there's many ways in which you could do this, but I want you to think about this and just think.
3 linearly independent vectors, or however many.
A set.
Any set. Okay.
However many you can find. 4 if you can find them. I don't know. Good luck. However many linearly independent vectors you can find. And I want you to keep thinking about this while I talk about my second example, which comes from graph theory. Okay? And here what I'm going to do is draw a graph for you. Okay? So let's say that the graph looks like this. Okay, so my graph has 4 vertices. Here they are. It has 6 edges, which I'm going to label A, B, C, D, E, and F. Okay? So there's my graph. And again, I'm going to give you a task. And in this case, what I want you to think about is how you can choose a bunch of edges choose a set of edges of the graph but I'm not going to allow you to form cycles. What do I mean by a cycle? Well, exactly what you might imagine. Just walking around and going back to where you started. So if you do this, then you made a mistake. This is not allowed. Okay. And of course, there's many ways of doing this again, but I want you to think about some of those ways. And now I'm going to ask you a bunch of questions about these 2 problems. Okay? My question 1 is a Sesame Street question. You know that song of Sesame Street that says one of these vectors is not like the others. So which one of these vectors is not like the others? What do you think? F. Some of you say F. Would any of you say something different? You might have different reasons for giving me a different answer.
I could say A.
F?
A.
Maybe A? Of course, that's a very big question. So let's see what that question actually means. Why? Well, let's take a vote. Which one do you guys think is more not like the others, F or A? So who thinks F is the most not like the others? Don't be shy. Okay, and who thinks A is the most not like the others? So there's some votes for this one, but most of you think that it's F. And what's the reason? It's the 0 vector. Why is the 0 vector different from the other ones? It's orthogonal to everything.
Well, in the context of your question, no vector is linearly independent from the origin.
In the context of my question, what happens with this vector F? You're never going to choose it. F is useless.
In both cases.
Why? Because what does it mean to be linearly independent? It means you do not have an equation, a linear equation of the form something times this vector plus something times this vector, so on, equal to 0. But if you are silly enough to choose vector F, then you have an equation F equals 0. You cannot do that. F is useless. I can never choose it. Okay. I think that's why most of you told me that vector f is not like the others. And of course, my question 1 prime is which one of these edges is not like the others. And if I asked you to choose one of the edges that is not like the others, I think most of you would also choose edge f. First, because visually, look at it. It's just this weird edge that goes out and then goes back to itself. Okay? But in the context of this question, of course, f is special because you never want to choose it. F forms a cycle with itself. You can never choose it. Okay. So that's good. That's an answer to my first question. Now let me push this point a little bit. Which other one of these vectors is not like the others? And we agree that f is very different from the other ones. Now, if I ignore f, then which one is different from the other ones? Some of you gave me an answer already, which is a. And why is a different from the other ones? Where
All of the other ones lie on the same plane, but A doesn't.
right.
It can be
You can.
any
A is so useful that you can always choose it. No matter what you've done, you can always choose A. Why? Because these guys are all on a plane, and A is independent to all of them. A is super useful. Super useful. I can always choose it. That's what makes vector A special in this vector configuration. And of course, question 2 prime, you can probably guess what the question is and what the answer is. Question 2 prime, in my graph, which other one of these edges is not like the others? Well, even if you just kind of read this, you don't even have to look at the picture and see that's the right. I mean, you barely have to look at the picture and see that here also A is super useful because you can always add it, and it's never going to cause you to form any cycles. A is super useful. I can always choose it. Same answer. Okay. Third question. Which pair of vectors is not like the others? You think D and E. Why are these two special in a certain way? Well, because when it comes to the point of choosing a set of linearly independent vectors, then you either choose one or you choose the other. But you can't choose both. Because if you were to choose both, you would have the equation E equals 2D. So in a sense, they are, I don't know, I might call them twins. Because you can always either choose one or choose the other, but not both. They kind of play the same role.
You can't always choose one.
You can't.
Starting out, you mean, like this, as your first choice.
So what I mean is this: if you're building your set,
Yeah.
and at a certain point you ask yourself, okay, can I add D? Can I add E?
Yeah.
Then the answer to that question is the same. Okay.
Yeah.
So
okay,
either
I
you
see.
can add both of them,
Uh-huh.
or you cannot add either one of them.
Yeah.
Which is why I say that they always play the same role. Either you can add one of them, and it doesn't matter which one, or you just can't add them at all. I can say they play the same role. Okay. And of course, this is exactly the same in the situation of my graph. Because if you are thinking about adding D or adding E, then either you can add either one of them or neither. You can't add both because you would make the cycle DE. And if in a certain situation D would form you a cycle, then E would form you the same cycle. So D and E are twins. They play exactly the same role. Okay. So what's the point that I'm trying to make in asking you these simple questions? The point is that I think this is the first time in your life that you have seen on the same whiteboard a linear algebra problem and a graph theory problem. And not only that, but it turns out that the answers to those problems are exactly the same. Okay? And what matroid theory is able to do for us is to understand why, even though these look like different problems, they're actually exactly the same problem. Okay? And matroid theory is going to give us the background to attack them at the same time. Okay? Let me give you a third example. And this third example comes from something called matching theory. Matching theory. Okay. So I'm going to ask you to imagine that there's a little town. And there's some men in the town. And there's some women in the town. You can probably guess what the names of the women are in this town. Called A, B, C, D, E, and F. These are the men. These are the women. Let's call the men 1, 2, and 3. Okay? Let me say that these are very naive men. I'll explain why in a second. And for the students in Colombia that might not know this word, naive is iluso. Very naive men. Why? Because these men are all single. And what they're going to do is that they're just going to say, okay, who would I think it's time to settle down. Who am I willing to marry? And they're just going to make the list. Okay. And this person is really picky, and he says, I'm only going to marry A. She's the love of my life, and I would only marry her. Okay. Or maybe I might marry this guy. I don't know. Oh, but then he thinks, oh no, I'm in the U.S. and in the U.S. you can't really do this, and in Colombia you can't do this either, and so he's just going to marry A. Period. It's the only person he would be willing to marry. 2 says, okay, I also want to marry this one, but I might also marry this one or this one. And 3 is not so picky at all. He just wants to marry as soon as possible. Except that F is 10 years old and it's a little 10 years old. He's not that much of a desperate case. But these men are very naive because they think that they can basically get together and just plan who they're going to marry, and the women are just going to agree. Okay, little do they know what's going to happen. But anyway, the point is that these guys want to get married. And what they're going to do is they're going to basically have a meeting where they just decide who each one of them is going to propose to. Choose a set of women to propose to. Okay? And hope that they will say yes. I should say again, both in the US and in Colombia, polygamy is illegal, and so they cannot both propose to the same woman. That wouldn't make much sense for their interests. Okay? What's the point of this example? Let's go back to here and think about the same exact questions. Which one of these women is not like the others? I think you would immediately agree that it's the 10-year-old. 10-year-old cannot be married, and so according to these chauvinistic, naive men, she's useless. That's what I wrote here. She's not useless. She's just 10 years old, so you can marry her. They can never choose F. Okay? Now, if I made you choose another one, then who is the next most special woman here? You see, A seems to be beautiful and talented and smart, and everybody wants to marry her. Yeah? A is, I shouldn't have written here super useful. I don't but they can always choose A. I mean, no matter what has happened so far, they can always say, okay, whoever isn't married yet is willing to marry A. So, of course, she's going to say no to all of them, so maybe she's not so super useful. But which pair of women is not like the others? You see,
Yeah, because D and E is either going to marry 3.
D and E have exactly the same people willing to marry them,
Right.
but then B and C also, right? Okay.
But B
I
and C
mean-
can both get married.
But
But
that's
you can never choose both D and E. You can choose both B and C.
Right.
Yes.
D and E.
thank you. I kind of got lost on the board here. I should have completed my sentence here, and I never did that. They play the same role. You can choose one or the other. One or the other, but not both. And in this example, D and E play that role. Only 3 is willing to marry them, and it doesn't matter whether 3 marries D or marries E. They play exactly the same role. B and C play different roles because they can both get married at the same time. Okay. And so this is another example where even though superficially the problem is very different, really bottom down, the problem is exactly the same. Okay. This is the history of matroid theory. Some people were interested in linear algebra, and they came up with a definition of something that they wanted to call a matroid. Some people were doing graph theory, and they came up with a definition of something that they wanted to call, I'm not sure if they gave it a name, but then they found out that it was exactly the same structure. And then different people came to study this problem of matchings. And of course, I'm talking about men and women, and maybe this sounds a little fantastic, but this is really a very relevant example in real life, where you want to maybe assign, for example, medical schools and medical school applicants, I understand, do it this way, where medical schools they talk to each other and make sure that they can both be they can all be as happy as possible, at the expense of the poor students that just have to wait and see what will happen to them. Okay. And so these are 3 situations that seem very different, but the tools of matrix theory will apply to both of them, to all of them, and we will see that next time. Okay. So it's probably a good place to stop. See you guys next time.